Hi. My name is Marc Emmerich, and I'm the CEO of Emmerich, which is a battery company. And yeah, it's great to be here today to talk about our battery systems and the electric systems for motor gliders. So yeah. So just the schedule, I'll be talking about Solo and Emmerich, which is a partnered company. I will do a brief history of electric gliders, and then I will talk about the challenges during the development of the battery systems for the self-launching gliders of Jonker, Schemp, and Alexander Schleicher, and what is up and coming in the next years for us. So Solo, you might know it because it's a staple in the gliding industry. This company was founded by my father, Wolfgang Emmerich, who unfortunately died at the beginning of this year. This is his glider flying, and he pioneered some of the engines that the glider community is using. And until last year, he worked every day on the company. So a short history: they did the turbos, the sustainer engines, and then in '83 they started doing self-launching capable, and then in '98 it was certified. And since '23, actually, Solo is also doing electric systems. And Solo is a certified company doing design, manufacturing, and maintenance, which is our European equivalent of the FAA. Emmerich is my company, and we started doing batteries in '21, and we produce certified battery systems for gliders now since '22. And as you can see in the exhibition hall, we work with all the three big manufacturers and also smaller ones to come to bring batteries to the market for the glider community. And we also do rapid prototyping for other aircraft. Like, some people are crazy enough to build air taxis with electric engines or 10-seaters. So we provide batteries for them as well as hydrogen hybrid aircraft. So just a very brief history of electric gliders. Of course, many of them are left out, but just some of the certified gliders are in here. So one of the pioneers was the Antares, who had a really good system very early on with batteries in the wings. It was not such a big series production, and that was also because there are many different variants on the market. And what was a bigger market was then the FES system, which I don't actually know exactly when it started. Maybe Luca can tell me. In 2009. Okay, I couldn't find it on the internet. So there are various models equipped with the FES. And then at around 2020, we started to certify battery systems for the wings for the Schleicher aircraft. And then a little bit later, fuselage batteries for the Jonker aircraft. And now this year, also for the Schemp Ventus aircraft. So now we come to the development. So basically the kickoff of the development was that before 2020, batteries were put into aircraft and they were not really certified because the EASA was not able and the FAA was not really there with the technology and would tell us how to certify the batteries. So that led to a few incidents where they changed their mind and tried then to find a means to certify these batteries. For example, the Boeing incident, where Boeing tried to sort the cells by X-raying them to find the bad ones and sort them out. But that didn't really work. So we had to find means for passive safety. The picture in the bottom right is actually not a battery-powered airplane, so they can burn as well, just as a reminder. So what we did was I was invited by a professor from Mosbach, Rainer Klein, to a panel with the EASA, where I made a suggestion for a certification venue for a certification path for batteries, which is now in 2023 part of the special conditions that were issued in 2014. So there is now a way to certify batteries for gliders, for motor gliders. And basically what we have to do is to blow up a full-scale battery and actually not blow it up at the same time. So we trigger one cell and make sure that there is no propagation to the rest of the battery. The battery is preheated, the battery is fully charged, and we do this and we repeat this 3 times. So that's the way, and there should be no fire or smoke coming out of the battery, except in the designed venting path. So when we start developing batteries, we looked at different cell formats, and they all have their advantages and disadvantages. So you can use a cylindrical cell that was developed for flashlights and powered drills and stuff like that. They are produced in quite high numbers, which makes them very reliable. There's also pouch cells, which are a little bit more vulnerable and need an external casing, external structure to work. And prismatic cells, who are really easy to assemble because they are basically just bricks that you put together. But they also are a big entity. So if one of these cells goes bad, when you are up in the air, you have a big portion of your battery burning already, which limits your chances of going back to the runway safely. So that's why we chose to use the smallest cells that are available that have a high energy density. And it's actually quite obvious when you think about it. A cell in a critical event is basically just a pressure container that you want to vent in the right direction that you designed it for. And yeah, so it's like a rocket that is unintentionally burning up the fuel inside. At the same time, when we were doing this, NASA was also developing batteries for their spacesuits. So they had the same challenge. They wanted to achieve the same goal, to have one bad cell not affect the other cells. Actually, when we saw or when we read what NASA did, it was after the development, or development was basically done. So our heart stopped almost because we thought we would learn a lot new, but basically we came to the same conclusions. So that was good because we did almost the same tests, but not as detailed as NASA did. So yeah, so if you try to build batteries, you have different technologies to put them together, to make the contact to the bus bars. And all these design considerations affect the safety of the battery later on. You can do wire bonding like Tesla did. You can do resistive welding with a fusible link like NASA did, or laser welding, which is the most economical way to do it. Yeah, so one of the principles is that in a battery you have a series connection and you have parallel connection. And one of the problems is when you have a permanent connection of the parallel cells to each other, if one cell heats up, it will heat up the other cells as well, because they will dump the energy through the affected cell that has a short circuit and heat up in the process, and they will also heat up the affected cell, which creates more and more energy and causes the propagation in the end. Whereas when you have fusible links between the cells, they will break when the current rises, and thereby electrically isolating the cell and stop the buildup of heat. So that's also what we did in the design. Yeah, so what we did also is we blew up a lot of cells. So we blew up hundreds of cells in order to find out how they fail. And we did this by heating them up, by overcharging, or by nail penetration. And here you can see as an example, we prepped the cell, we wrapped it in our compound, and then we blew it up. So this is just an example of test specimens that fail differently. So a cell can fail in a lot of different ways, and it's a very chaotic process. It's very stochastic. So the cell can pop, it can vent through the top, it can vent through the bottom, it can do multiple of those things at the same time. So that's all, we had to consider all these failure modes in order to design a safe battery. Then we went to subscale testing to do a proof of concept. And yeah, as you can see, we did it in a parking lot, which is actually not allowed, but it was the Corona time, so nobody was there to stop us, which was really good for the battery testing, because now we couldn't do all this. So that was advantageous. This is near the university in Stuttgart, where we are situated. And yeah, we have a battery container, so we store the batteries outside of the building for safety, which I would also recommend you to do if you have a battery-powered glider. Don't store them at home, because you don't have 100% safety, and they are really a fire risk if they go bad. So here you can see one of the test specimen where this is basically the last iteration of the technology. We have a wrap around the cells, we have fusible links, and some other means, and that means that the failed cell will not propagate. There is we work with latent heat. That means that there is a phase change. This material around the cells is injection molded, but it contains a lot of mineral where water is released that stops the propagation by consuming the heat in the phase change. And then you see that the other cells in the pack are not affected. And we did quite a lot of these tests to at least have a sample that will represent, go to 80–90% certainty that what we did as tests is also relevant in real life. And here you see that the cells that surround the affected cell are basically, except from being charred a bit, are basically intact and will not provide energy anymore, but will not burn up your airplane. Here you see a natural plot of the tests. You see the affected cell going up to 450 degrees on the cell can. And you see that all the other cells are also getting hot, at least at the surface, for a short amount, but then they cool down again, and the battery goes down to 50 degrees in total. And here you see one of the batteries from the side, where you can basically see the components. So I just want to take you through the design a little bit. You have basically a lot of cells in there. You have a battery management system around it that is distributed into 9 modules. And you have a venting part on the bottom left that will push out, or that will be the designed venting path in case of an emergency, if one cell goes into thermal runaway, and release the gases. And yeah, then in the front you have the main connector. You have a relay, so the battery will disconnect itself depending on basically the parameters that we set. If the battery is not thinking it can provide energy, or it's too dangerous, or the current is too high, then it will stop This is a 400-volt battery module. That means in this little suitcase, we basically have a complete 400-volt battery that is normally in a complete car. That means it's very tightly packed, and it's also a little bit complicated, but it ensures the safety because the layout is basically the same as you have in your electric car. The technology is the same. So then we went to full-scale testing. Actually, the wing batteries were tested first and certified first. And we had a much harder time certifying the fuselage batteries, the suitcase type batteries, than the wing batteries, just because they are more spread out and thereby easier to control. So here you see a thermal runaway of a cell and the release of gas and smoke through the exhaust pipe that was connected to the bottom exhaust vent port. Unfortunately, this is not a video because I couldn't cut it. It's a very long video. But yeah, I think you can see how it's releasing the gases. And we did this in test containers. Yeah, also to not pollute the environment, we collected everything and put it to a recycling plant. Here you can see an infrared image of one of the early tests that went bad. So it helped us a lot to have infrared video of these tests to determine what happened exactly. So we could really deconstruct what happened during the failed test and find the reasons for it and change the design just slightly to help us get through testing. Here you see a battery, exactly the same battery after it burned up quite a bit. So actually, because the design was already very robust, the propagation happened very slowly, but it still happened. So we had to change the design from there. So the battery was then submerged in water, because if you don't submerge it in water completely, you will not stop it from propagating, if it's already propagating. Because the only thing you can do is remove all the heat that is produced from it. But submerging it in water will also then cause more problems. So it's not really stopping it, it's just cooling it down. Yeah, so when the battery is installed in the glider, the vent port is actually connected to a vent pipe that goes out of the glider. The same is true for the wing batteries. So the wings have a certain breaking point where they will release the gases. And the certification regime requires 15 minutes from between the incident and your safe landing. So if the battery burns up after that, it's still certifiable. I can say that our batteries stayed cool even after 15 minutes, but still, that's a certification requirement. So what you do, when your instrument says you have a thermal runaway, what you do is you land immediately. So you put in everything that breaks your airplane, put the nose down, and try to find a landing place. That would be, so if you can land in 2 minutes, that's even better. So then just a quick video of a takeoff of a Junker JS3 with the RES system. Yeah, so that's just for illustrative purposes. So yeah, so to wrap it up, basically what Emmerich provides is a toolkit principle. That means we can build batteries in any shape, and we use the same parts and the same technology, so that for every different airplane that has a different need for a different size or shape of the battery, we are able to provide a solution that is certifiable. That's our goal, to do rapid prototyping in that way. And yeah, because we have basically the single cell as an entity, we can design every shape. We don't have a module. Oh, that's just a gimmick, but it's actually meaningful in a project. Yeah, and of course it always comes with the safety concept. So our idea is, so we did now batteries for the gliders and are in the market. And we want to, and also we are doing prototyping, as I mentioned at the beginning. So the idea is that we transfer the experience from the gliding world into the other CS-23 LSA space aircraft, because they will have a much longer time to certification if they economically go there. And then at the same time, the technology can also trickle back down to the gliders. So that's a little bit the idea also behind the company, to enable rapid development of batteries for aviation in total. So what you see here also is, for example, a air taxi and a 10-seater. So some people are developing 10-seaters currently that do ferry flights or island hopping, which is totally possible with batteries at the moment. And the last plane on the right is a hydrogen hybrid electric plane that is also currently in development in Germany. It's a 2-motor plane, and it's quite exciting. So yeah, what do we plan for gliding next? First, we want to make sure that our current system is really reliable, and we think it's already quite reliable, but of course there are some children diseases that we have to fix. And so we also rely on our customers, and for the US, especially Leo, here to facilitate the transfer of information from the owners to us, so we can fix everything that occurs and make the system really really tough. Then we want next year to develop bigger batteries for the 2-seaters and open class gliders, and also then certify a more powerful system along with that to bring the bigger gliders in the air. For that, we have now the opportunity to have new cells that are little bit higher in energy density since we started. But the development of batteries is not really quick. So there is a slight increase every year. The batteries are now more powerful. They can endure lower temperatures and higher temperatures, and they live longer, which was very much driven by the car industry, probably. But the energy density did not really increase so much, but it's still increasing. So there is still development, but it's a slow evolution. And when we see that there is a maybe 30% increase to the current technology, we would like to recertify and increase the energy. But that's definitely economically driven, because it's quite expensive to certify a battery at the moment. So, for example, the Yonka battery, the fuselage battery, we had to blow up 5 of them just in order to get to the final design. Yeah, so our partners, we have partnered up with also research institutions, and then the glider manufacturers, and Solo, who is putting the system together with a Form 1. So yeah, University of Stuttgart, of course, where we also try to get resources into the development of these batteries. Yeah, so that rounds it up.
Do you see, are the increases in density happening just through better engineering of lithium ion? Do you see any chemistry changes coming in the next 3 years that can get us another 20% or 30%? Where are the increases coming from?
Yeah, the increases are coming from everywhere. So definitely. When the cells, for example, they get a little bit safer, then we can use less overhead in designing the battery. So that's a venue. Then the newer cells, they have more silicone in the active material. That is basically increasing the energy density, but also making them die earlier if you use that energy. So it's a little bit, yeah, we don't know if that's really the way to go for now. Yeah. Mm-hmm.
Can you speak about the temperatures, minimum and maximum tolerance?
Yeah.
What happens with the battery getting hot?
Minimum and maximum temperatures. So the cells have an operating temperature range of around -20 to +65 degrees. When you discharge the battery, that's about the range you have. If you charge the battery, they want to be at +20 degrees to 40 degrees for maximum life. So at the moment, we don't have heating installed, but in the next iteration, and also in various prototypes, we did it already, we want to include a heating. So if you want your battery to live long, you charge it at 20 to 40 degrees. The battery will not charge below 5 degrees Celsius. It will prohibit it.
Mark, when I charge my JS30 RES, and if I leave it past 100%, I see it balancing, and it says about 0.6 millivolts, more or less, plus or minus, is a difference. If I do a partial charge from 90 or 95, it stops at around 20 to 30 millivolts difference. Can you speak to, are you monitoring individual cells, and if the voltage difference between individual cells is too much, what happens?
Yeah, so the voltage difference between the cells is usually an indicator for the health of the battery, because at the beginning they will be very close to each other. Then they leave the factory, and then they can drift apart a little bit again, and then you have to balance them again because there is an initial degradation that is not really symmetrical on all the cells. After that, you should not have an increase in drift or in a difference of voltage. If you experience that, you should contact us.
Okay, so I've experienced an increase from 67 to 21 millivolts over the past 3 charges. Now, do I need to keep charging to 100% to allow them to balance, or is that already an indication of an issue?
No, you should try to balance them.
How do I balance?
You just charge them up. So at a certain voltage, at around 93%, they will they will start balancing.
So around 390 volts, they'll start balancing.
Yep, exactly.
And I can let it go until the charger
Stops. Exactly. The charger will stop when they are completely balanced. To talk to the temperatures, 1 second. The maximum temperatures, because you mentioned that we don't have cooling. So we calculated that the batteries can do all the missions without cooling, and cooling would introduce more weight. So you would have a less energy in your battery and also a complicated system. So we said we don't use cooling and instead just put more cells in, which is in the end more practical. Yeah.
How hot does the thing, if you run maximum power until the battery is discharged, what is the elevation of temperature that you have?
You don't do that normally. You would just take off with maximum power. Yeah, sure. It really depends. So if you start at around 20 degrees Celsius, you would experience maybe a 40 degrees increase. Then you would experience the same, more or less, but because the cells will be a little bit less resistive at that state, but you will experience the same. So yeah, at around 65 degrees, you should try to cut down the power. Latest. 65 is the normal range, but if you can go higher, you can go up to 75 degrees, but that will be detrimental to the longevity of the battery.
What is the cause of the thermal runaway?
Yeah, so the cause of a thermal runaway is that one cell has experienced a degradation of some kind or a material defect that is sometimes happening very early in the process. So there is some impurity in the active material in the paste that is put on the collectors. The manufacturers are getting better at making sure that it doesn't happen, but it still happens. So it's just a numbers game. So your battery will eventually burn. Unless it dies before that, for age. Yep.
It seems like the circuit
Yeah, so the battery is actually doing the charging itself. So the battery is controlling the charger and requesting current. And if the charger is not behaving correctly, then the battery will cut off the connection to the charger.
Who sells you? I forget who does the blue wrap. Who sells you? Can you tell me who cells you're using?
Which cells?
Yeah.
Oh yeah, we are using Molicel cells. Molicel, it's a Canadian, it's a NCA.
NCA.
Yeah. Molicel, it's a Canadian US company. Yeah. So?
So you're making lots of different modules and different configurations.
Yeah.
So if I have a self-launcher with one module and the battery pack goes bad, how long does it take to get a replacement? Do you stock, you have stock replacements in stock and all these configurations?
Yeah.
Or do you have to custom build them? How long would that take?
We don't really have so many variants. So for the gliders, we have the BM384, which is for the Jonker gliders. Then we have the BM384B, which is for the Schempp gliders. And we have the BM480, which is the wing battery for the Schleicher gliders. So it's only 3 variants, and we have them. We don't have them in stock, so we produce them on demand. But for example, Leo will have them, maybe 1 or 2 of them in stock.
Currently 4 in stock.
So the dealers would have generally.
I can't speak for the other brands of gliders, but for the Emmerich battery used in the JS3, we generally have several in stock.
Yeah, and because they are certified, we cannot make batteries for every different glider. We usually have the same, and also the chargers will accept all batteries.
I know that there was a firmware upgrade of some sort to the
Yes.
JF. How often do you think you're going to be, batteries are going to need to be upgraded, the firmware, the charging system?
At the moment, we don't think that we need to upgrade the batteries, but if there is an accumulation of bugs of some sort, we want to do it definitely, but not every year. So yeah.
Can you talk about the engine control unit? I know that you went to liquid control in some designs, and other designs have just heat sinks and stuff. Are they evolving as well, or what do you think the next step is for the ECU?
They are evolving, but I would point you to a talk by Jason.
Jason's talking about the electric glider landed out in a farm pond.
Yeah.
So keep in mind, Marc is primarily involved in the batteries. The integration of the system, which is a solo system, and the control elements, he's familiar with them, but it's not his wheelhouse.
Okay.
All right, I don't know if you want to try to answer that, or I can.
Also, I'm going to speak a little bit about that in my talk.
Okay.
About a JS glider.
I'm going to talk about the specifics of the control problems, which was the question.
This gentleman, please.
If you were to ship a battery, the form factor that Schleicher is using,
Yes.
how would you do that?
Actually, we don't ship the batteries. We ship them to AS, and they would do the shipping for you. So you can ask them. Yep.
What kind of incident management did you describe? Is it typical for the glider to be undamaged?
Sorry, to be?
Is it typical for the glider itself not to be damaged?
Yes, from the tests, we expect that. So there is a level of uncertainty about it. For example, we test the battery fully charged, heated up. There are other scenarios possible, maybe 50% charged, not heated up. We don't know exactly what happens because we would have to do a lot of samples. That is economically unfeasible. We would love to do more, but from my understanding, let's say, and from my experience during testing, I think the glider would be undamaged. It would vent, it would then cool down again, and you can take out the batteries. So that's what the tests told us. No, no, they should not.
You said in the beginning you should rather not store the batteries at home.
Mhm.
But where else should I store it? Keep it in the hangar?
Yeah, you can store them everywhere. So the best SOC state of charge to store them is 50%. That's the optimum. That's where the battery experiences the least stress on the chemical stress. And then you want to store them maybe above 0 degrees. I'm really a little bit uncertain about lower temperatures, but I think what I heard from the literature is that above 0 degrees is best. And then charge them as warm as possible. So think of battery cells as a human being. We have the same comfort temperatures. Yeah. Yeah.
What's kind of a rule of thumb number these days for the energy density
Yeah.
that you can achieve kilowatt hours per kilogram?
Yeah. So on these batteries, these are high power batteries. We have a very the gentleman asked about energy density of batteries, gravimetric, I guess. So that means the energy density of the cells is at around 250. For high power, it's more like 230, but now getting up to 260 in the new developments. And then the battery will have between 175 to 200 watt hours per kilogram, depending on if you have a high power battery like us or a high energy battery that can be discharged slower. And then again, it depends also on the profile. So if you draw a lot of current, you have less energy in there.
And then what sort of powertrain efficiency?
Powertrain efficiency, for the total system. So the batteries are around 90%, and then from what you put in at this power level, and the whole drive system, the rest is also at around 90 to 91%. The motor controller and motor together are at around 90 to 91% at the moment. Just the controller is 95 or 94. Yeah. Mm-hmm.
Is there a downside? I mean, if you actually were using it as a sustainer to get home,
Mm-hmm.
and you ran the batteries all the way out, is that, all the way down, is there a downside to that? Does that decrease longevity of the battery?
You can use the battery all the way to 0%. The battery will protect itself, so it would switch off before you reach critical low voltage.
I understand you can run most of these systems in single battery or double battery configuration.
Yeah.
Do you not get a wear imbalance, or how do you deal with the wear imbalance from one battery potentially being repeatedly in single cell?
This is something actually we don't know exactly, because this has to be driven by experience. I guess that it's not a problem because the healthier battery will provide more power when they are together then, because the internal resistance of the battery will be lower. We manage the batteries in a way so that they are switched on and off depending on the voltage, so that when you discharge, you start with the higher battery, and then the lower battery will connect when it reaches the same voltage. The same applies for charging, but yeah, other way.
So then if you had one battery in very good condition and one battery in very bad condition, can the battery in very good condition then not provide much more power than it was designed to, for example, your cell phone?
We have kind of a buffer in there. So you would have around 50 to 60 amps per battery in a normal takeoff, and it can do 80 amps. It's designed for 80 for continuous use. Yeah.
I assume these batteries will eventually fail and die over time. Are they going to be rebuildable, or do we pretty much send them off to recycling and buy new ones, or
Yeah.
as they degrade, can they be rebuilt themselves and things like that?
We can rebuild the battery, but we will not put individual cells in and out, because that's not going to work, because then you have this aging problem, which is on a parallel set, it's not a problem, but in a series connection, it's a big problem. So we would refurbish your battery with a complete new set of cells, and the rest, the management system and so on, you could keep. Mm-hmm. Yep.
I've had a situation case I really need something. I was still 800 foot in the glide, the day was dead. And I decided to save in case I needed the last minute. When I turn it back on just to check, well, actually, I now always leave the controller on all times. I'm monitoring battery temperature throughout the entire flight. I'm never turning it off.
Mhm.
But it seemed to have picked up more capacity after resting for about 20, 30 minutes during that glide. Is it good to save and build capacity and have capacity that way, or is it a myth?
No, it should not. It should not build up capacity. So what you maybe experience is different ways of calculating the state of charge. So we have basically 3 algorithms that we use depending on which situation you are in to calculate the SOC, because there is no direct measurement how much energy is left. You can only approximate it. So we use the voltage in certain cases. We count basically the amps that go in and out. So, and we also adjust that over time. So if you have a charge, if you charge up the battery and you experience a disconnection of the battery or a low voltage warning before it reaches 0%, we have to readjust the nominal capacity. But maybe this case we can have a chat later. You can explain what happened, and I try to find an explanation. Or maybe it's a bug.
The controller efficiency again.
Mhm.
You said 94, 95%. Does that efficiency remain over the entire temperature range? So for example, when you get your 400 temperature range, is it still the same?
The motor controller is pretty stable with temperature.
And what about the load? So is the 94, 95% only rating, that rating only for the maximum load? It doesn't go down as you reduce the load, or does it stay around?
It is pretty stable. Yeah, that's a little bit more complicated, but it's a very narrow band of efficiency. Also for the motor. The motor is at 95, 96% for all the operational range. The battery gets more efficient if you draw less power. Yeah. Okay. Then I want to conclude. I'm here for the convention, and if you have a question anytime, you can ask me anytime.